So this is chapter 3 of the book by Prigogine, Entropy Production and the Second Principle of Thermodynamics, or the Second Law of Thermodynamics. In the first section, we study the differences between reversible and irreversible processes. Consider some time-dependent physical process. Now, if the equations describing the process are invariant with respect to the change in sign of the time variable, the process is called reversible. If not, the process is called irreversible. For example, let's take the specific case of the wave equation. So this equation, equation 1, describes the propagation of a wave in free space. It could be, for example, an electromagnetic wave. We see that in this equation the time variable comes in as the second derivative with respect to time. So that's like coming in as t squared. So if you put minus t or t in this equation, the equation stays identical. Therefore, the propagation of a wave in free space is a reversible process. Now let's take another example, which is the Fourier equation for temperature, which is equation 2. This equation describes how the temperature changes with time at a given place in the system. And we see in this case that time variable comes in with the power 1. So if you put minus t in this equation, you will get a different equation. So therefore, we are talking about an irreversible process, which is the flow of heat in this case. Indeed, most physiochemical processes, such as diffusion, conduction, whether of heat or electricity, chemical reactions, etc., are irreversible processes. That is, they are described by an equation similar to that of equation 2, where the time variable comes in with a single power. So changing t to minus t gives us a different equation. These are all irreversible processes. Therefore, we need a theory of irreversible thermodynamics to treat these processes. And that is the essential point of this book, is to treat these irreversible processes. Now we are going to study what is meant by the word entropy. Entropy is a variable which defines how the conserved quantities of nature, for example energy, momentum, angular momentum, charge, etc., are distributed over the microscopic degrees of freedom in the system. So the greater the distribution of these conserved quantities over the microscopic degrees of freedom, the greater the entropy of the system. And of course, for an isolated system, which can reach equilibrium, in the equilibrium state, the entropy is a maximum. Entropy, the word entropy comes from this Greek word written here, which means evolution. And in fact, that is a good name for this variable, thermodynamic variable, because it in fact does describe the evolution of the system. Now let's postulate the following properties of entropy. Number 1, that is, it is an extensive property of the system, which means that it is additive. The entropy of the whole system is the sum of the entropy of its parts. 2, we can define the change of entropy of the system as being made up of 2 parts. 1, the change in entropy due to that entropy which is coming in or going out of the system to the external environment, is sub-indice E, plus another part which is due to the production of entropy within the system due to irreversible processes which are occurring within the system, this second term of this equation, which has the sub-indice I for internal to the system. Now for reversible processes which are occurring within the system, there is no change in entropy of the system. So DIS is equal to 0 for reversible processes. However, for irreversible processes, there is an entropy change due to that process occurring within the system. And therefore DIS is greater than 0 for irreversible processes. Now for an isolated system, we do not allow any movement of energy or mass into the system and no work to be done on the system. So there's no exchange with the external environment. So then by the previous equation, the term DES is equal to 0, and so we just have that DS, that is the change in entropy of the system, is equal to DIS, that is the change in entropy due to the internal processes occurring within the system, irreversible processes occurring within the system, and so that is greater than or equal to 0 by the second law of thermodynamics. It is equal to 0 only in the case that we are in equilibrium. Now it turns out that DIS is greater than or equal to 0 is the most general evolution criterion of natural processes. There are other criteria, for example, the free energy. In this case, the Helmholtz free energy F is equal to E, the internal energy, minus T, the temperature, times S, the entropy. And this decreases when irreversible processes occur. However, functions like the Helmholtz free energy F or the Gibbs free energy G exist only for very specific conditions. For example, in the case of the Helmholtz free energy F, it decreases only at constant temperature and volume. Only if we have constant temperature and volume can we say that the Helmholtz free energy for the system is going to decrease. And similarly, for the Gibbs free energy, only in the case that we have constant temperature and pressure can we assume that the Gibbs free energy is going to decrease as the system moves towards equilibrium. So the most general evolution criterion is that of equation 3, that the change in entropy is positive definite, or that is the second law of thermodynamics. This holds under any condition. Now we are going to consider the local formulation of the second law of thermodynamics. So now consider that we have a system 1 inside a larger system 2, such that the global system is isolated. The second law of thermodynamics says that the change in entropy of the global system is just equal to that, because entropy is an extensive variable, of the sum of the two changes in entropy in the two parts. So ds is equal to ds1 plus ds2, and by the second law of thermodynamics this has to be greater than or equal to 0, equation 4. Now let's postulate what is known as the local formulation of the second law. That is, not only does equation 4 have to be satisfied, but in fact that the entropy production due to internal processes which are occurring in system 1 has to be greater than or equal to 0, and that internal processes which are occurring in system 2 also has to be greater than or equal to 0. This is known as the local formulation of the second law. So that means, for instance, we cannot have situations in which, for example, the change in entropy due to irreversible processes in subsystem 1 is greater than 0, while that due to internal processes occurring in subsystem 2 is less than 0, even though the sum, remains greater than 0, as in equation 4. So this is known as the local formulation of the second law of thermodynamics, and results such as equation 6 are excluded. So that means there is no possibility for compensation in every macroscopic region, which means regions which have on the order of 10 to the 23 particles, or that microscopic fluctuations are negligible. The entropy production due to irreversible processes is always positive in these macroscopic regions. Now, we can have interference of irreversible processes, but only is this possible when they are occurring in the same macroscopic region, and we'll see some examples of that later on in the book. So the local formulation of the second law, as represented by equation 5, is the law on which this course is based. And this local formulation of the second law has been verified through statistical mechanics and experiment. Now, please note that this local formulation of the second law does not mean that we cannot have ds1 greater than 0. That means the change in entropy, the global entropy or the total energy of subsystem 1 greater than 0, while the change in entropy in subsystem 2 is less than 0, or the reverse, because there is a flow of entropy allowed over the boundary of these systems if they are open or closed to one another. It is only the case for the irreversible processes which are occurring within the systems 1 and 2 that they have to be greater than 0, greater than or equal to 0, like specified in equation 5. Now let's consider in detail what is meant by the absolute temperature. We have been using this variable temperature before in the course, but now we're going to describe a little bit more the characteristics of temperature. So let's now consider a closed system containing a single component, and we assume that there are no irreversible processes occurring within the system. So it's a closed system which only allows the flow of energy over the boundary. So the change in entropy then is defined by ds is equal to dq over t, equation 7. And this of course comes from the Gibbs equation, in which we have put dn, that is the number of moles, change in the number of moles being equal to 0, because we're not allowing material to flow in or out of the system, and there are no chemical reactions occurring in the system which are going to be changing components, because in fact there is only one component in the system. And also the change in volume is equal to 0. So this equation 7 just comes from the Gibbs equation, where dq here refers to the flow of heat over the boundary of the system from the external environment, and T of course is the absolute temperature. Temperature T satisfies a number of characteristics. Number 1 is that the temperature is positive definite. We don't have any negative temperatures. Temperature is also an intensive property of the system. That means that its total for the system is not the sum of the parts. That is, the temperature is defined in each region of the system. We also assume that we can measure it by measuring some arbitrary parameter, for example, the electrical resistance of a wire, for example, in the system. We also assume that T, the temperature, is a function or can be related to an empirical temperature for the system. For example, measuring the resistance of a wire. Now, to fix the scale for the absolute temperature, we need 2 points. The first point is the temperature at absolute zero, which we assign 0. The second point is the triple point of water, that is, the temperature at which water can exist as a solid, a liquid, and a gas, which is 273.16 degrees. So these 2 points, 0 and 273.16, define the scale for the absolute temperature. So note that also the change in entropy of the system is just equal to dE, the change in the internal energy, plus P dV, which is the work done on the system, over the absolute temperature T. That comes out from equation 7, substituting for dQ, which is equal to dE plus P dV. Now let's calculate the entropy production due to a particular irreversible process. And this particular irreversible process will be the flow of heat. So consider two closed subsystems 1 and 2. So the total system therefore is also closed. And these two subsystems are maintained at uniform temperature T1 and T2 respectively. Now the entropy being an extensive variable means that the global entropy for the global system, or the global change in entropy of the global system, is just ds is equal to ds1 plus ds2. Now for each phase of the system, and when Prigogine talks about phase, he is meaning subsystem. So for each subsystem, we have, for example, d1q is equal to d1iq, which is the flow of heat internally in the system, that would be from 2 to 1 or 1 to 2, plus d1eq, which is the heat coming over the boundary of the system from the environment. And the same is the case for subsystem 2. Therefore, for the whole system, or the global system, because it is a closed global system, the change in entropy of the global system is just equal to d1q over t1 plus d2q over t2. Now, just substituting equation 10 into equation 11, we arrive at equation 12. And how do we get the last term in equation 12? Well, obviously, the flow of heat from subsystem 1 into subsystem 2 is just equal to the negative of the flow of heat from subsystem 2 into subsystem 1. That's why the minus sign appears here. Therefore, we can divide the change in entropy for the global system into two parts. First part, dEs, is equal to the entropy which is flowing over the boundary of the system, the closed system. So that is equal to d1qE, which means from the external environment, the flow of heat from the external environment into subsystem 1, plus dq2E, which is the flow of heat from the external environment into subsystem 2 over their respective temperatures, of course. The second component of the change in entropy for the global system is due to the irreversible process which is occurring, which of course is the flow of heat. And that is just from the second or the last term of equation 12, just dIs is equal to d1qI times 1 over t1 minus 1 over t2. And so this is the entropy production due to the irreversible process which is occurring, which is the flow of heat from subsystem 1 into subsystem 2, or leaving subsystem 2 and going into subsystem 1. So we have calculated the entropy production for this closed system due to the flow of heat from subsystem 1 into subsystem 2, which is given by equation 14. So now, empirically, we can show that the entropy production for this irreversible process, that is the flow of heat, which is given by equation 14, is always positive definite. And that is because we know that heat flows. Empirically, we have established that heat flows from a hotter component to a lower temperature component. So for example, let's say that subsystem 2 is the hotter, the warmer temperature than subsystem 1. Then 1 over T1 minus 1 over T2 will be greater than 0. And in this case, since T2 is the hotter subsystem, heat will flow from T2 into T1. So D1Q will be greater than 0. So we have two greater than zeros, so the multiplication of D1Q by 1 over T1 minus 1 over T2 will also be greater than 0. So in other words, by equation 14, the entropy production is greater than 0, as we expect, which is the local formulation of the second law of thermodynamics. Now we can do the same thing if we assume that T1 is greater than T2. So 1 over T1 minus 1 over T2 will now be less than 0. And that means that heat will be flowing out of T1, which is the hotter subsystem, and into subsystem 2. So D1Q will be less than 0. The change in the heat in subsystem 1 will be negative. And in this case also, we have D1Q being negative and 1 over T1 minus 1 over T2 being negative. So the multiplication of two negatives will give positive. So again, the production of entropy is positive definite. And we should note that entropy production is only 0 when we reach thermal equilibrium. That is, when T1 is equal to T2, then there will be no flow of heat, and so we will get the entropy production being equal to 0. Equation 14 will be equal to 0. So now to get the entropy production per unit time, we just divide equation 14 by dt on both sides, t being the time variable. And then this is by the second law, greater than or equal to 0, which is equation 17, which comes directly from equation 14 by dividing by dt, the time variable. So now note that equation 17 is a product of a rate of an irreversible process, d1q by dt, where t is the time variable, which is the flow of heat. So it's a product of the rate of this flow and multiplied by the function of state, which is 1 over T1 minus 1 over T2. So this is a very general form that we will find for every irreversible process. The production of entropy is just the multiplication of a flow and what we define as a corresponding force, which in the case the flow of heat is just 1 over T1 minus 1 over T2. So that, if you like, is the force which is giving rise to the flow of heat. So this is a very general form which exists for all irreversible processes. That is, the production of entropy is just a flow times a force, the corresponding force. And this is greater than or equal to 0. Equal to 0 only again in thermal equilibrium. So now we want to go towards determining the entropy production for the flow of material. In the previous section we studied the flow of heat. Now we're going to be studying the flow of material. But before we do that, we have to define the entropy of a multi-component system different material components in the system. And so this means defining the chemical potentials. So here in equation 18 we write the generalized Gibbs equation for the case in which we have a change in energy, change in volume, and a change in the number of moles of component gamma. Mu gamma are the chemical potentials which are defined by mu is equal to minus T, the temperature, times the partial of S with respect to partial N gamma, where we hold the energy, the volume, and all the other components, moles of the other components, fixed. That's why we have N prime gamma. So equation 19 then is the definition of the chemical potential, and it's just proportional to the partial derivative of the entropy with respect to the number of moles of component gamma. Now the chemical potentials are also intensive variables, just like 1 over the temperature, which is partial S with respect to partial E, E being internal energy, or for example the pressure over the temperature, which is just partial S over partial V. So the intensive variables are defined as differentials of different extensive variables. For example, the entropy, the energy, and the volume are all extensive variables. Now there are other ways to express the chemical potentials when other variables are held constant. For example, in the energy representation, the chemical potential of substance gamma is just a partial of E, the internal energy, with respect to partial of N, the number of moles of substance gamma, holding, in this case, the entropy, the volume, and all the other mole numbers constant. Now we can also define the chemical potentials in terms of other variables, for example, the enthalpy, H, the Helmholtz free energy, F, and the Gibbs free energy, G. And you can derive these for yourself, these equations 21. So these are just different ways to represent or to express the chemical potential as a function of these different thermodynamic variables. And please try to show that equations 21 are correct. Now it's possible to derive other relations involving the chemical potentials. For example, these relations in equation 22, where this small s, small v, and small h are respectively the specific molar entropy, the specific molar volume, and the specific molar enthalpy of component gamma, as defined by these equations, equations 23. So you can prove equations 22 by using the definitions which are given in equation 23. So this is simple algebra using the definitions equation 23 to derive equations 22. And you can do that to convince yourself that equations 22 are correct. And we will be referring back to these relations at other points in the course. So it might be useful to really do this yourself. Okay, so now what are some characteristics of the chemical potential of component gamma? Well, for ideal systems, we find that the chemical potential can be divided into two parts. One part, which is the zeta function, as a function of pressure and temperature, and the other part dependent on the molar fraction, this big N gamma, which is just the number of moles of substance gamma over the total number of moles of all the components in the system. So that is the mole fraction. And the relation, the empirical relation, is given by this equation 24. So we have the chemical potential being some function of the pressure and temperature times, plus R, which is the universal gas constant, times T, the temperature, times the logarithm of the mole fraction. Now for ideal gases, and remember that ideal gases are gases made up of particles which have zero volume and that only interact at zero distance, and they have an infinite potential at that zero distance for their interaction. So for these ideal gases, which in some cases is a good approximation but not in all cases, to the real systems, we can write this zeta function, this function of pressure and temperature, as being equal to the universal gas constant R times the temperature times the logarithm of P, the pressure, plus some other function of the temperature. So we can divide again this system, this interaction between ideal gases. And this zeta function can be divided into two separate parts, one depending only on the pressure and the other only on the temperature. Now for the case of non-ideal systems, we cannot use equation 25, and we find that the chemical potential can still, however, be divided into two parts. One, the first part, depending on the pressure and the temperature, and the second part, depending again on the mole fraction. But now we introduce what is called an activity coefficient, F sub gamma. So this is the expression for the chemical potential for a real system, a non-ideal system. In section 7 of chapter 3, we are going to study the entropy production of a different irreversible process. And this process is going to be chemical reactions. So chemical reactions are irreversible processes. They only proceed in one direction. And here we're going to be studying the affinity and the coupling of chemical reactions, only considering for the moment closed systems. So let's determine the expression for the entropy production due to a single chemical reaction occurring within a closed system. So using equation 2.6, which shows that dG, that is the change in the advancement of the reaction, is just dN by the stoichiometric coefficient divided by the stoichiometric coefficient mu for component gamma. And using equation 18, which is the Gibbs equation, we can write ds is equal to dq over t plus A times dG by T, the temperature, where A is the affinity of the chemical reaction. So this is the definition of the affinity, and it is related to the chemical potentials by A is equal to minus the sum over all the components in gamma in the system times the stoichiometric coefficient gamma times the chemical potential mu gamma, equation 28. So equation 28 is the definition of the affinity for the chemical reaction which is occurring. So here again, the total entropy change of the system can be divided into two parts. The first part, due to the flow of heat coming over the boundary from the external environment, that's dq over t, equation 29. And the second part, which is due to the chemical reactions which are occurring within the system, which is just the affinity times dG, the advancement of the reaction, over the temperature. And remember, the entropy production for any irreversible process has to be greater than or equal to 0. So that gives us equation 30. And so you can prove, just as we did for the case of the flow of heat, that for chemical reactions, we always have positive definite production of entropy. So try to prove that for yourself, just the way we proved it for the flow of heat if you go back a few slides, you will find our description of how the entropy production is always positive definite for the flow of heat. Now we know that in equilibrium there are no net chemical reactions occurring, which means that the affinity for the chemical reaction must be equal to 0. And affinity, as we defined it, is just minus the sum over all the components in the system of their stoichiometric coefficients times their chemical potentials. So this has to be equal to 0 in the equilibrium state. Now this equation, equation 31, will lead us to equation 32 for the case in which we have not chemical reactions occurring, but the substance changing from phase 1 to phase 2, for example, liquid water to a gas. In the case that we have an equilibrium between the two systems, for example, gas over liquid, then we have to have that the two chemical potentials in those two phases, liquid and gas, being equal. And that is equation 32. And that comes from equation 31 in equilibrium. Now, dividing equation 30 on the previous slide by dt, this incremental time variable, dt, then we can derive the entropy production for the chemical reaction is just 1 over T times A, the affinity, times V, where V is dG by dt, which is the rate or the velocity of the chemical reaction. And this has to be greater than 0 by the second law of thermodynamics. So this gives us an equation 33 for the entropy production due to the irreversible process, which is chemical reaction. Now you have shown on the previous slide that A and V, the affinity and the rate of the reaction, always have the same sign. So the right-hand side of equation 33 is always greater than 0. And it is a product again of a chemical reaction rate, V, and the corresponding force, which in the case for these chemical reactions is just the affinity over the temperature. So it has the same form as that of the production of entropy due to the flow of heat, just a flow times a force. The flow for the chemical reactions is the rate or the velocity of the chemical reaction, and the force is the affinity over the temperature. Remember that in the case of the entropy production due to the flow of heat, the flow was the flow of heat, and the force was 1 over T1 minus 1 over T2. In the case of several simultaneous reactions occurring within the same system, then we just sum over all the reactions rho which are occurring within the system to get the total change in the internal entropy of the system, which is equation 34. So we are just summing equation 33 over the different reactions which are occurring, where now A in this case, the affinity, depends on the reaction, and it is a sum over the stoichiometric coefficient for component gamma in reaction rho times the chemical potential of component gamma. And if we have a system which is in equilibrium, then all the affinities for all of the chemical reactions occurring within the system will be equal to 0, which is equation 36. To get the entropy production per unit time for a system where there are multiple chemical reactions occurring, we just sum over all of the chemical reactions. The affinity times the rate, the affinity really over the temperature times the rate. So force times the flow. And that again has to be greater than 0 by the second law of thermodynamics. However, we could have the system undergoing two simultaneous reactions such that the affinity of reaction 1 times its rate is less than 0, while the affinity of reaction 2 times its rate is greater than 0, as long as the sum of these two are greater than 0, as long as they are occurring within the same macroscopic region. So therefore we have this coupling of the two reactions, 1 and 2. So therefore one of the reactions can go in a direction in contrary to what is described by its own affinity. And this coupling of two distinct irreversible processes is of very great importance in biological processes. Another example of coupling two distinct irreversible processes is that of thermodiffusion. This is the diffusion of matter against its concentration gradient. And this results in a negative entropy production, but this effect is compensated by the positive entropy production due to the flow of heat. So we have two processes occurring. One is the flow of matter, and the other is the flow of heat. And we can have the concentration gradient increasing in matter due to the flow of heat, which compensates for the negative entropy production in the case of the diffusion of matter. So now you can suggest three other possibly coupled irreversible processes which might be occurring in biological systems or in other physical phenomena. They don't have to be specifically biological. This happens very frequently in the cell, for example, the living cell. So try to think of three other possibly coupled irreversible processes in which one of them is reducing the entropy of the system. For example, this separation of matter into a gradient of matter. And that can occur because there's another process which is coupled, for example, the flow of heat, which produces more entropy than the other process reduces. And so we still satisfy the second law of thermodynamics, but we have the production or the construction of ordered systems. So this is the first time we really see how non-equilibrium thermodynamics or irreversible thermodynamics can be used to explain some very interesting biological facts